It's an honor again to be at Black Hat. So today I'm going to talk about work where we tested implementations of the Wi-Fi handshake. And this work was done in collaboration with Domien Schepers and Frank Piessens, and they were both also working at University KU Leuven at the time. So first, a quick background. We see that lately more and more Wi-Fi networks are employing encryption. For example, in the graph here, you can see that in 2010, nearly half of all networks were using wireless encryption. So you can see the green line at the top, that's the amount of network that employ some form of encryption. If we then look at the beginning of this year, we can see that around 75% of all wireless network were using some form of encryption. And the most important part here is that all these networks rely on the four-way Wi-Fi handshake to generate fresh session keys. So even networks that, for example, use a pre-shared key, or you have an enterprise network, they all rely on the Wi-Fi handshake and in particular on the four-way handshake. So it's absolutely critical that this Wi-Fi handshake is securely implemented. Otherwise, your network or your clients might be vulnerable. So if we look at the related work in this area, we can see that the design of the handshake has already been formally verified as secure. So we are quite sure that that should be good. So I do want to remind you here that just because this design was proven secure, it could also be that there are some flaws in their proofs, but for now we're going to assume that the design is secure. And instead, in this presentation, we're going to look at implementation flaws. So there has been a very limited amount of related work in this area. So there has been one paper which fuzzes the initial stage of the Wi-Fi handshake, where beacons on probe requests are used. But the limitation is that this work only looks for common programming mistakes, such as buffer overflows or double freeze or null pointer dereferences, which crash the implementation. Additionally, they only check the first stage of the handshake. So we are not looking for logical vulnerabilities, and we are also not investigating the full Wi-Fi handshake. And that will exactly be the goal of our work. We're going to study the Wi-Fi handshake in detail and try to detect logical vulnerabilities. So not just vulnerabilities that crash the implementations, but cases where an implementation deviates from the specification. So in order to explain this, I'm first going to introduce the Wi-Fi handshake and how it works. So as I mentioned, the Wi-Fi handshake is used mainly to negotiate fresh session keys, which are then used to encrypt actual data traffic, which is transmitted at a later point in time. The Wi-Fi handshake is, of course, also used to discover networks using beacons on probe requests. And additionally, it is also used to select the cipher that you want to use. And it prevents against downgrade attacks as well. So like I mentioned, after this handshake, actual Wi-Fi traffic is encrypted using a specific algorithm. And these days, this algorithm is either Wpa Tkip or AES CCMP. Now, Wpa Tkip is rather insecure algorithm, and that was because it was designed to run on old web hardware. So at the time that web was designed, it was found to be completely broken, and companies and vendors wanted something more secure to run on this old hardware. However, this hardware was not very efficient, so they came up with a new standard, but they had to sacrifice some security in order to be able to run on this old hardware. And that's where Wpa Tkip comes into play. However, these days we have modern hardware, so you can run proper encryption algorithms, and in the case of Wi-Fi, you should only be using AES CCMP. Okay, so how does the Wi-Fi handshake actually work? So the first stage of the handshake, we are basically going to discover nearby networks. And this is traditionally done by the access points, which constantly transmit beacons, which announce the presence of a network. The client monitors for these beacons, and when it has found a network it wants to join, it will decide which cipher it wants to use, and then it will send an association request to the access point that is basically saying, hey, I want to connect to this access point. So Once the client has sent this association request, which again informs the access point, hey, I'm a client and I want to connect, if the access point accepts this client, then it will send the first message of the handshake, and then the client will reply. Now, essentially, these two first messages on the handshake are used to transport random nonsense, and these random nonsense are used to generate a fresh session key which has never been used before, so we don't get key reuse. So as you can see here, the client generates its session keys once it received message 1, and the access point will generate the session keys once it has received message 2. Then in the second stage of the four-way handshake, there are two more messages that are exchanged, and a bit simplified, these messages essentially try to protect against downgrade attacks. So in particular, in message 3, the access point will send its supported list of ciphers in a secure and authenticated manner. So by now the access point has a session key, and this message 3 is protected using the session key. And the idea here is that when a client receives this message, it can verify the cipher list that is in message 3, which is authenticated, and an attacker cannot forge this list, and it will compare it to the cipher list that was in the beacon, because the beacon contains no crypto and can be forged by an attacker. And if there is a mismatch between these lists, then a downgrade attack was detected. And finally, at the last stage of the handshake, the client sends message 4 to the access point, which basically informs the access point, hey, I didn't attack a downgrade attack, we're good, let's start exchanging normal data traffic. Now, one thing I didn't mention yet is in message 2, the client also transports the cipher that it chose in a secure manner. But this is just to make the handshake more robust. So you can see at the access point right there, it will also verify the chosen cipher of the client, but this is just to make the access point more, to make the handshake more robust. If the access point, misses this check, that doesn't mean there's a downgrade attack yet, because we still have the second check. Okay, so the next thing you need to know is how are these messages defined? Well, they are defined using EAPOL frames, and simplified, this is the layout here of an EAPOL frame. Basically, you have a header with the destination and the source address. You have some flag which identify the message that we are dealing with. For example, is it message 1, 2, 3, or 4? You also have a MIC. The MIC here stands for Message Integrity Code, and this is used to verify the authenticity of a frame. In other words, so that an attacker cannot decide to flip bits in this frame or decide to forge a message. And finally, there's a field called key data field, and that's encrypted. And it is used to transport, for example, this list of cipher suites in a secure and authenticated manner. And it can also transport the group key, which is used to encrypt broadcast and multicast traffic. So we're almost done with the background here. There's one more thing I need to explain, and that's how a Wpa Tkip frame looks like, because we're going to use parts of this in our attack. So you can see a very simplified layout here, and the idea is basically we have some data that we want to transmit. We calculate a MIC over this data. So a MIC again stands for Message Integrity Check, so it assures the authenticity of the frame that no bits have been flipped. And this whole frame it will be encrypted using RC4. So you should know by now that RC4 is an insecure algorithm. You should not be using it, and this is one of the reasons why Wpa Tkip is not as secure. There's another reason why Wpa Tkip is not secure, and that's because this MIC check here, it's calculated using a MIC key. So it's using a hash algorithm, essentially. But the problem here is that if an attacker is able to gain access to the data and MIC field in a decrypted form, so if he can somehow undo the RC4 encryption, then if an attacker simply has access to this data field and the MIC field, he can derive the MIC key. And normally that is not possible in a cryptographic protocol. And we're going to come back to this issue later during the presentation. For now, we have covered the background, and we can finally start explaining how our testing methodology actually works. So the way we are going to test implementations of the Wi-Fi handshake is using model-based testing. So model-based testing is already fairly well known, especially in the academic world. And lately, it has also been applied to test the implementations of network protocols. So just a reminder, what do I mean with model-based testing? Basically, you have an implementation, a program that you want to test, and you also have a formal specification that describes how the implementation should be behaving. And then you're basically going to check, is the implementation indeed behaving according to the specification, according to this abstract formal model? And a few years ago, this technique was applied against SSL on TLS, for example, in the paper, The Messy State of the Union. And the researchers there discovered a lot of issues, and the worst of these issues could be used to completely decrypt any TLS traffic. And the idea in our work now is to come up with a variation of this approach which we can apply to the Wi-Fi handshake. Again, with as goal to detect logical vulnerabilities in the handshake. So, how does our approach work? Well, we basically first start with a normal execution of the handshake. So in an execution where we can successfully connect to the access point, everything goes okay. We take that basically as our base point. And then we modify this normal execution of the handshake. For example, what we can do is we can decide to drop random messages from the handshake. And if we do that, the handshake should no longer be successful because we didn't send all the required messages. Another thing that we can do is we can try to retransmit messages. And in that case, the handshake should still be executed perfectly fine because it's very normal in a Wi-Fi network that frames are retransmitted because, for example, the acknowledgement was lost. And these modifications to the Wi-Fi handshake, to this normal execution of the handshake, we call these test generation rules. So a test generation rule is, for example, a rule which says try to drop every message of the handshake or try to inject random messages between a normal handshake. So what we need to do here then is define appropriate test generation rules so we can test the necessary functionality of a Wi-Fi handshake. Now I will give some more example of these test generation rules. But one important thing I do want to mention now is that we assume that all these modifications to this base execution of the handshake are applied independently. So we're not going to combine two different test generation rules because otherwise we would be in an explosion of the number of options. It would be an exponential options that we get, which would be basically impossible to execute them all. So we're going to assume they're independent. This is a limitation of the approach, and we're working on it to remove this limitation, but currently that's what we're doing. So once we have our test generation rules, we basically apply all these test generation rules to our model, to our normal execution of the handshake, and we end up with a test case. So in our work, what is the definition of a test case? A test case essentially specifies the messages that you want to send to the implementation under test and the replies that you expect in return. But that's not everything that the test case defines. It also says whether this should result in a successful connection with the access point, for example. Because you might have a case where you always get the expected replies, but it should not result in a successful connection. For example, if you drop the last two messages of the handshake, well, you will always get the expected replies, but the handshake hasn't finished yet. So you're not allowed to connect yet. You're not allowed to send data yet. So to recap, a test case defines the messages that you send, that you expect, and whether this should result in a successful connection. Okay, so we now have our test generation rules, we have our test cases. How are we going to execute the test cases? Well, the idea is actually very straightforward. It's like normal test cases, you basically execute the test case. If during this execution you get an unexpected reply, you immediately know that something is wrong here. You don't yet know whether it's a vulnerability, but it's definitely a bug because there is a deviation from the standard. And you're going to track these, in a sense, failed test cases. You're going to save those. And after the test case has been executed, you're going to reset the implementation under test by sending a deauthentication frame to, for example, the access point or the client. If we always got the expected replies, then we're going to check if it was a successful connection or not. And if we get the expected result, then again, everything is fine. And we can ignore this test case because the implementation reacted in the way it's supposed to, so we don't need to investigate anything. But if we get an unexpected result here, for example, if the test case says that we should not end up with a successful connection, however, we are able to send data frames, then something is wrong. So to clarify here, the way we test whether a connection is successful or not is by sending ARP frames to the implementation under test, and if we get a reply back, we know that the handshake succeeded. So the idea is here that we now end up with a set of failed test cases, and we're going to inspect these test cases. So the way we can do this is that if we don't have access to the source code of the implementation, we can run additional black box tests and try to determine what exactly went wrong. If we have the source code, then we can try to inspect the source code and see what the cause of the problem is. And once we know what the bug is, an expert can then determine whether this bug is exploitable or not. So to come back to the test generation rules that we have used, we basically have two broad categories of test generation rules. The first one, they manipulate messages as a whole, and they are the examples that I already mentioned, that you can drop a message or that you can repeat messages, and you can then see how the implementation reacts to this. The second set of test generation rules, they don't manipulate messages as a whole, but they manipulate certain fields or properties of a message that is being sent. For example, we can use an invalid replay counter, we can modify the header. For example, we can modify the header and say that this is message 3 while it's actually message 2. Or we can send an invalid MIC, so an invalid message integrity code, and we can do other stuff as well. We can also mess with the list of supported cipher suites or the selected cipher suite, which is normally authenticated in the handshake. So that summarizes our testing technique on a high level. And we applied this technique to 12 access points in total. And we tried to get a good variation in the type of access points that we tested. So for example, we have open source ones like OpenBSD, like Linux implementations. We also have code of home routers where the source code was leaked. So there's old code of Broadcom and MediaTek. And there's also the traditional closed source implementations like Microsoft, Apple, and so on. And we also try to test two more professional access points, namely the ArrowHive implementation and also an ArrowNet, which I think was from Cisco. And the results here were very surprising in my opinion, because the Wi-Fi handshake is fairly simple. I mean, you have this stage where you discover a network, and then you just have 4 messages which are exchanged. So I expected that we weren't going to find much. But we discovered several issues. So that was a very nice success. And I'm going to briefly discuss some of the more interesting issues we found. And these issues are also the exploitable one. So generally in every access point we found some small deviations from the standard, but some of these deviations were just very benign, and you can't even consider them really bugs. But they were deviations, but yet some were bugs but non-exploitable. But we're going to focus on the most interesting ones. So the first one is that the MediaTek and Telenet implementations, they don't properly defend against downgrade attacks. So what is Telenet here? Telenet, it's a Belgium ISP, and they hand out their own home routers with an implementation of the Wi-Fi access point. And here we found that they do not check the chosen cipher that the client sends in message 2. So as I mentioned in the introduction, this check here is only to make the handshake more robust. Or to put it differently, although this check is missing, I'm not able to come up with an actual attack which abuses this. However, inspired by this result, I noticed that the MediaTek also has a client-side implementation of the Wi-Fi handshake. And then I manually inspected the source code, and I found that MediaTek was also missing the client-side downgrade check. So it was missing both checks. And in this case, you can trivially downgrade a MediaTek client. So the way this works is an attacker would put up a rogue access point, and it would clone the real network, and it would only advertise support for WPA Tkip, which means the client is forced to select the cipher because it's the only option. Normally, this attack would have been detected at this stage because an attacker cannot modify message tree because it is authenticated. However, MediaTek doesn't check it, so it doesn't notice that anything is going wrong. So for the second attack that we found, it is a denial of service attack against Windows 7. So on Windows 7 and also on Windows 8 and Windows 10, you are able to set up a hotspot. So a normal infrastructure access point, you can set that up on Windows 7. And here we found denial of service attack, which it's very interesting because we can target a specific client using this denial of service attack. So the way this vulnerability works is if the client sends an association request to the access point, then everything is fine. Because sending one association request is normal, it is used to inform the access point, hey, I want to connect. But if we then send two rapidly after one another, something goes wrong on the access point. Because normally it should now start the four-way handshake because it received the association request, it should either deny this connection or it should start the four-way handshake, but nothing happens. And if we now, some seconds later, try to reconnect, so we again send an association request, then we get an association rejected response. In other words, we cannot connect. The interesting part here is that if a different client tries to connect, then everything goes just fine. It sends the association request, and the access point will start the four-way handshake. So although we don't have access to the source code here, what we conjecture that goes wrong here is that the access point is keeping state associated to client 1 here, and this state somehow gets corrupted because we sent two association requests right after one another. And because then this state associated to the client is corrupted, it can no longer connect. And of course, an attacker can abuse this. He can spoof the MAC address of the victim and then send two association requests in name of the victim. So the proof of concept code of this attack is online. I also have a recorded demonstration of this attack. If there is time at the end of the talk, I will show it. But to make sure we don't run out of time, I'm going to show it at the end of the presentation. So if you follow this GitHub link, you will see the proof of concept code of several other attacks, including some attacks against OpenBSD implementation as well. Okay, so let's go on to the next attack. The next attack is a downgrade attack against Broadcom. And the vulnerability that we exploit here is that the implementation of Broadcom cannot differentiate basically message 2 and 4 of the handshake. So what do I mean with this? Well, if the access point is expecting message 4, but it's actually receiving message 2, then it will simply treat message 2 as if it were message 4, and it will successfully complete the handshake. Now, I'm not going to go into detail about how this attack works. You need a few tricks in order to carry it out. But the core message here is that we can abuse this to downgrade the access point into using WPA Tkip. So we cannot downgrade the client. We can only downgrade the access point into using a weaker cipher. And this is of course bad because the access point will then start transmitting data frames encrypted using WPA Tkip, which uses RC4, and it's not that secure. Now the reason why I find this attack very interesting is because if you read the Wi-Fi standard, the official specification, it says that message 4 serves no real security purposes. It says message 4 is only there to ensure reliability. In other words, if you would drop message 4, you would still be fine. However, our tech clearly shows that if you don't handle message 4 properly, you can downgrade the access point. So here, essentially, not only did we found an implementation flaw, this also uncovered an incorrect claim in the Wi-Fi specification. So now to the more interesting part of our examples. We have also tested the OpenBSD implementation of the Wi-Fi handshake. And here we found several issues as well. And in the first issue, we are able to perform a denial of service attack against the access point. And this is based on two vulnerabilities in the implementation of OpenBSD. The first vulnerability is that OpenBSD never stops the Tkip countermeasures. Now, what are these Tkip countermeasures? So, like I mentioned, WPA Tkip is not that secure, and in particular, if you can obtain a decrypted WPA Tkip packet, you could derive the MIC key. And the designers of WPA Tkip realized this. They realized, hey, the protocol that we have here is not that secure. And what they decided to do is they decided to detect active attacks against this protocol. And if they notice that an active attack is going on, the access point will stop all traffic for 1 minute. So this is, of course, very interesting behavior because the official specification says that if there's something strange going on, you should halt all traffic for 1 minute. And in other work, we have shown that this connection can actually be triggered by a third-party attacker. So this on its own, it's already basically a flaw in the standard. But for OpenBSD, this flaw is much worse because it doesn't just stop the traffic for 1 minute, it stops the traffic forever. So all that we need to do now is we need to find a way to trigger these MIC failures. So these MIC failures happen when, for example, the client receives a WPA Tkip message where the message integrity code is invalid. And if that happens, the client will send a so-called MIC failure report towards the access point to inform the access point, hey, I got a strange corrupted message here, maybe I'm under attack. And if the access point receives 2 of these messages, then it will stop all traffic. And in case for OpenBSD, it will stop it forever. And here the second vulnerability comes into play. Namely, the implementation of OpenBSD accepts these MIC failure reports even before the 4-way handshake has been executed. In particular, even before these fresh session keys have been negotiated. And we can combine these two vulnerabilities in an unauthenticated terminal denial of service attack. So how does that attack work? Well, we have our first stage of the attack, where everything happens normally. So we have our attacker here, which acts as a client. We have the access point of OpenBSD. The client simply searches for the network. It sends an association request saying, hey, I want to connect to the network. And then the access point will send message 1 of the 4-way handshake. But normally the client would now send message 2 of the handshake. However, when we're going to execute our attack, we're going to send this MIC failure report. And this MIC failure report is also authenticated using a MIC value. However, the key that we're going to use here is just an all-zero key, so an array of all zeros. And why are we going to use that? Well, because the access point hasn't generated the session key yet, because it hasn't received the real message 2 of the handshake, meaning currently its session key is memory, and memory is just an array of all zeros. So of course, we can then forge this message. It will be accepted by the access point. And if we then send that message again, the access point will have received 2 MIC failure reports, and it will start the Tkip countermeasures. And in case of OpenBSD, these countermeasures last forever. The only way to stop it is to reboot the access point. So to be clear, this has already been patched by OpenBSD. And I'm now going to try to give a demo of this attack. So let's hope you can first get the screen online. So we had some trouble with this. I hope they can now show my screen. Let's give them a minute. But okay, that does not seem to work. So I will try again at the end of the presentation and try to use some different settings. For now, let's just continue with the presentation. Okay, so you can download the proof of concept code online, and I will also put a video of this online as well. Okay, so let's continue with the second attack. On this attack, in my opinion, is really the most interesting one. Namely, we found a man-in-the-middle attack against an OpenBSD client. So after observing this issue in the OpenBSD access point, we inspected the source code, and we found that the client has a much worse issue. Namely, it's simply missing the complete state machine of the protocol. So what do I mean with this? What I mean is that the client will process any message you send to it, even though it shouldn't be accepting this message. So for example, if you just send it any message in the handshake, it will handle it. Now this is very surprising because the code of OpenBSD is actually of high quality. It doesn't have any buffer overflows, it doesn't have any double freeze. At least in the Wi-Fi code that I looked, it's well written. However, the state machine is missing, so even though your code is very good, this still voids and throws away all security that the Wi-Fi handshake is supposed to provide. So how does this man-in-the-middle attack work? We again have our client here, and now we are targeting the client, so it's the OpenBSD client that we are targeting, and we are setting up a rogue access point. The idea here is that this rogue access point just advertises, it basically clones the real network that we want to attack. The client will then connect to our rogue access point. It will send an association request informing our rogue access point, hey, I want to connect, I'm a client. And normally a real access point would now start the four-way handshake. But what we're going to do is we're going to send message 1 of the group key handshake. So what's the group key handshake? The group key handshake is in a sense similar to the four-way handshake, except that it's used to transport the group key, which is used to encrypt broadcast and multicast traffic. So the interesting part here is that we have a very similar vulnerability to the previous case, where because the client hasn't generated the session key yet, it will use, again, an all-zero key to verify the authenticity of this frame. So as an attacker, we can easily forge this group message 1 frame, and the OpenBSD client will accept it. Once it accepted this message, it will reply using message 2 of the group key. And an interesting side effect of sending group message 1 is that it will also open the data port essentially. So at this point, the client will accept normal data traffic, and it will also send normal data traffic. Now, what's also quite bad about this situation is that not only are we now able to man in the middle this Wi-Fi client, because just to recap, normally the client also verifies the authenticity of the access point, but in this case it doesn't. The attacker doesn't need to know the password, yet still the client will successfully connect. But what goes wrong here, not only does it accept data frames, it never installed the key, meaning it accepts plain text data frames, and it also sends plain text data frames. So at this point, yeah, your security of the Wi-Fi is broken. Again, there is a demo of this online, and let's hope that at the end of the presentation, maybe the demos will work, and then I can try to do a live demo. Otherwise, unfortunately, that won't be the case. So as I mentioned, I only discussed the most interesting vulnerabilities that I found. We also found some other ones, and you can see them in our Whitehead paper and also in the academic paper that preceded this research. So we found things like basically benign irregularities where an implementation deviates from the specification, but this does not result in an attack. But you can use this to fingerprint an implementation, of course. You can determine, is this a Cisco access point, is this a Microsoft access point, or whatever. We also found other denial of service attacks, so those seem to be quite common. For example, a permanent denial of service attack against Broadcom, but you do need to know the password of the network to carry out that denial of service attack, so you need to have an insider threat. And against Windows 10 and Arrowhive, we also found another insider denial of service attack. So these attacks are, for example, problematic if you have a network like Eduroam or a network, for example, here like Black Hat, where everyone knows the password. You could take that network down. And there are also some other issues that we found that are a bit less interesting. So our approach is still quite limited in a sense, because our testing technique is quite basic. In other words, there are a few improvements that still can be made to our work. For example, we don't know how much code we actually tested. I mean, we are sending these messages, we are sending modified messages, but we don't know how much code actually is being covered. Additionally, we're only sending well-formed messages. And what I mean with that is that messages are, for example, never truncated. They always have the fields they should have, but those fields simply have invalued values. Another thing is that these test generation rules were applied independently, and we mainly tested access points. We also tested some clients if we thought that they were interesting to test as well. For example, we found a bug in the access point implementation. Then we saw, oh, this product also has a client implementation, maybe it has a similar bug. But we mainly tested access points. Now, the reason why I think that this is a promising technique, though, is because our current method is a black box testing methodology, so you don't need access to the source code, so you can test any implementation that you want. And another thing that this work shows is that searching for logical vulnerabilities is quite important. Because like I mentioned, the Wi-Fi handshake is fairly simple, yet still we discovered quite some issues, and that was surprising. So that leads me to the conclusion of this talk. These Wi-Fi implementations are less secure than expected, and I will believe that if we come up with more advanced testing techniques, we will uncover more issues. And not only in the Wi-Fi protocol, but also in other protocols. For example, in related work, similar methods have been used against TLS, and for example, OpenSSL and all the other libraries, and they all found bugs which sometimes lead to exploitable vulnerabilities. So that's that point. Finally, I have a short announcement, which is basically about follow-up work of this work. If you have a product which uses a client-side implementation of WPA 1 or 2, or another Wi-Fi handshake, you should talk to me because there's a good chance that it contains some flaw. So I'm going to try to do a demo again. Maybe it works now. Let me see if I can change the screen resolution, if that helps. There we go, excellent. So I'm going to show the man-in-the-middle attack against OpenBSD because that's the most interesting one. So let me first check that my wireless interfaces are still working. That seems good. Let's go to the other VM. Okay. Okay, so let's get started. We have our attacker here, which is represented by this Kali virtual image. And what we're going to do is we're going to start up the rogue access point. So you can see the configuration of this access point here. Basically, the SSID is a demo network. And by the way, if you don't want your MAC address to accidentally show up here in some of the debug output, disable your Wi-Fi. So just to be clear, there might be some information otherwise on this presentation, so disable it now. Anyway, the network that we are going to clone is called demo network, and as you can see, the attacker does not know the password of this network. So let's start this access point. And I am currently using a modified version of the Linux access point to carry out my attacks. Okay, so that access point has started. Let's now try to connect using here the OpenBSD client. So this is running an unpatched version of OpenBSD. And we are going to connect to the SSID demo network. And the client is going to use the password such secret while. And normally, the client should not successfully connect to the access point because these passwords are different. But let's see what works. No, we don't need that. So the client is now normally searching for the network. It's sending probe request, and it has connected. So you can see here, our OpenBSD client has sent the association request, and normally it should now accept message 1 of the four-way handshake. However, it receives message 2 of the group key handshake, and it will happily accept it and send message 2 of the group key handshake. So it first receives message 1, and it replies using message 2. And here we can also see this at the attacker screen. Some other people are trying to connect. Maybe I should show some MAC addresses. Anyway, we can see here that the client is trying to connect. The access point is skipping the four-way handshake. It's not installing the pairwise keys, and then it receives message 2 of the group key handshake, meaning that the attack worked. So by the way, whoever is trying to connect, it won't work because this is a modified access point. So let's confirm that we are able to now intercept traffic. Right, so let's start Wireshark here. Let's actually enable monitor mode, so we don't just see Ethernet traffic, but we see the full Wi-Fi traffic. Okay. Okay. Let's filter for traffic from our device. And let's now try to go to a website. So let's go, for example, to CNN. CNN still uses an unencrypted website, even today. This is a cached version from online, so we can see the client has connected. And if we then go to the attacker, we can see here an HTTP GET request. And this is indeed the one, it is to CNN.com. And we can, for example, see the cookies that are transmitted, meaning our attack indeed was successful. So, like I mentioned, OpenBSD hasn't installed a session key yet, meaning it sends unencrypted Wi-Fi traffic. And we can confirm that here. This frame is not using any encryption at all, so even you guys could see this request. Even if you are not an attacker, you can still see all this plain text data. And here we can confirm the protected flag is not set. So that concludes the demo.